Hello, and welcome to the last little bit of the chapter on alkenes. Let's see what we've got. We're going to talk about oxidation and reduction, often called redox. You may or may not remember this from general chemistry. It's not important if you do. But oxidation is when electrons are taken away. So zinc is being oxidized. If it goes from a zinc metal, zinc 0 to zinc plus 2, it loses 2 electrons. Reduction, that means when something is reduced, is when I go from copper plus 2 to copper 0. It's gaining electrons. In organic chemistry, we rarely do this. We rarely gain or lose electrons directly. However, we do often gain and lose the elements of oxygen and hydrogen. And this is a very nice definition. So oxidation, carbon is being oxidized, it gains oxygens. That's what you'd want those words to mean. Less obviously, reduction is the gain of H, or the loss of O, but the gain of H here, and that's what we're going to be looking at. So here I've taken acetylene and I've added 2 H2s, and I've formed ethane, and that is a reduction because it has absorbed the H2s. Okay? So here is an example in our chapter of alkenes. All by itself, this is a non-reaction. We can't take 2-butene and make it into butane because we can't do it, because the H2 is not reactive enough. However, if we look to the periodic table, and you can find this on your very own periodic table, this little snippet. If you look to the periodic table and you sort of grab a metal and you put it in with the H2, it helps break the H-H bond and delivers the goods. The most common catalysts are platinum, palladium, and nickel. I will use primarily platinum and palladium. Industry, strangely, uses primarily nickel. Sometimes we'll see the catalyst is supported on graphite. This is for ease of transportation, so that reads not palladium divided by carbon, but palladium on carbon. So there's carbon, which is a black powder, and then the palladium is in these little fine, impossible to see granules are stuck on the carbon. Anyway, what is the regio and stereochemistry of this H2 reaction? So remember, an alkene goes to an alkane. Regiochemistry. Sorry, this doesn't matter, right? I'm adding H and H, so there's no question of which carbon gets the H and which carbon gets the H. H adds to both. There is some stereochemistry. So if we had this very silly looking alkene and I added H2 to it, I would indeed get this cis alkene. However, you're really unlikely to see a reaction like this because you would need your alkene to be disubstituted on both sides, right? A tetrasubstituted alkene. If any of those C double bond C, if any of them have an H, then we're going to lose all the stereochemistry. So we won't worry about it. Okay, here's our next reaction. It's called, there are 3 in this video. As our next reaction is called dihydroxylation. Hydroxy is the OH group, di means 2, and this is obviously an oxidation reaction. Why obviously? My carbon is gaining oxygens. Okay? So I expect my oxidizing agents to be very rich in oxygen because they need to deliver that. There's 2 flavors to this. One is cis dihydroxylation over here. The second is trans. Okay? And these are diastereomers, so these are different compounds. And we're going to make them in 2 completely different ways. But it's nice to know that we can make both of them. Organic chemists like this kind of thing. If you continue on in organic chemistry, you'll see this a lot, where as soon as somebody comes up with a way to make one diastereomer, somebody else will need to find, well, how do I make the other one to make that complete set? We saw that before with HBr addition, where we have Markovnikov addition and anti-Markovnikov addition. And organic chemists like to learn these things together. So that's what we're going to do. Okay, cis hydroxylation uses this very strange reagent, osmium tetroxide. Osmium is not that easy to find on the periodic table. I think it's 76. I'm not sure. But it is the answer to the trivia question, what is the element with the greatest density? Is osmium, which I believe is 22 grams per cubic centimeter, which is pretty dense. So it's about twice as dense as lead, which is pretty dense indeed. Osmium tetroxide is extremely expensive and extremely toxic. I don't know which is worse, but you're really unlikely to see this in a lab unless you're a practicing chemist. However, you're in this class, and this is commonly covered, so we're going to cover it. So here's the reaction over here, is I take my osmium, and I have that second piece over there. What the heck's that doing? Well, what the osmium's doing is it's going to deliver the O's. But the OSO, the osmium-oxygen bond, is going to remain. And so in this next step, commonly called the workup, I have this reducing agent, which is going to cleave the OSO bond and put an H there. Do you have to remember all that? No. Do you have to remember the reagents? Yes. Okay. How do I remember this? Well, there's H2SO4. You certainly know what that is, sulfuric acid. And then I could replace one of the H's with the sodium, and it becomes sodium bisulfate, where the bi is a prefix for the H. H2SO3, rather than sulfuric acid, is sulfurous acid, and this is sodium bisulfite. Okay, so it's one fewer O, and then I replace an H with an Na. Maybe you don't remember that at all, then you just have to remember a random gibberish of letters, NaS, NaH, SO3. Okay? But I need that in the reaction in order to make it go, otherwise it doesn't work. Okay, here's our second reaction, is trans dihydroxylation. It starts with epoxidation, which is a fantastic reaction. I drew it a little funny, but it's okay. The two double bonds are, the CO bonds are cis to each other necessarily. There's no way to make a triangle where those would be trans. And I use this jumble of letters MCPBA. Most people use the jumble of letters because they do not want to write metachloroperbenzoic acid, and which has this structure over here. And if you were good with nomenclature, you would see that. So meta means that the chlorine is 2 carbons away. Chloro is chloro. Benzoic is that benzene ring. Benzoic acid is the C double bond OOH, and then it has the per to it. And if you'll notice that carboxylic acid has an extra O in there, just like hydrogen peroxide has an extra O relative to water. All these per means extra, and per this, per that typically means an extra oxygen, and that makes them good oxidizing agents. So what happens is the MCPBA delivers the extra oxygen to the cyclohexene, and the product is metachlorobenzoic acid, which we just get rid of. Okay. What's our second step? Our second step is to take this epoxide that we have generated and treat it with H3O+, which of course is the same as H2OH+, and that gets me the trans compound. Why does it not get me the cis? As we'll learn shortly, nucleophiles will come in from the back. Where did we see this before? We saw this before if the bromonium ion. Okay, so when we added bromine, we formed a triangle with a Br, and then the Br minus came in from the back to give us the trans product. Same idea, except that this epoxide is a stable compound, as opposed to the bromonium ion, which lasts for milliseconds or something like that. We'll notice that in this reaction, the H2O is acting as a nucleophile, and indeed, later on, if you continue in organic chemistry, you'll see that other nucleophiles add to epoxides. So of the reactions in this section, formation of the epoxide might be the most valuable, and that's extremely hidden because these dihydroxylation products are not particularly of interest to us. But you can see here's a nucleophile adding over here to form new compounds. And our last reaction of the three is ozonolysis. Lysis means to cleave. Ozone means ozone. And there is an ozonolysis reaction over there. And you see what's happened is the double bond was cleaved in half, and O's were put in its place. So it's definitely an oxidation. And it has a workup. And the workup can use either zinc or DMS. And what this does is it sort of soaks up the extra oxygen from the ozone. Years ago, I had a lab mate that had an ozonolysis explosion because said person did not include the zinc or the DMS. Your stuff will not explode on your exam if you do not include this. However, you might lose a point if you do not include it. This is a very common book question. I'm not particularly fond of it, but if you take other people giving you tests or standardized tests, you may see a question that sort of looks like this. They give you the products of ozonolysis and they ask you what the alkene is, and they like to make some kind of fancy roadmap problem where you detective work and you sort of figure out what things were. This was a very real thing, maybe World War II era kind of thing. This was a way to figure out what compounds were. Now we use instruments that help us do this. So that's our show for today. You'll notice that we had very little mechanistic information. All these reactions have mechanisms, but we're not going to go into those mechanisms over here. If you want to go to graduate school in organic chemistry, you can learn all of these things. Yay. But if you're not that interested in them, that's okay. But we still need to learn these reactions and need to learn what the products look like. And this includes the stereochemistry for the cis and the trans hydroxylation. And that should do it for our alkene chapter.